Okay, so let's start with the third part of the line integrals. So today, the topic, we will mainly consider the following question first. So find the potential functions. Okay, recall before we said that if recall if f is a conservative vector field, then this line integral can be computed by the following subtraction, where f is a potential function of capital F, or capital F is gradient f, and gamma A is the initial point, gamma B is the ending point. Okay, now, so a natural question is how to find f. Recall the example we showed before for the gravitational field. For that case, someone already tells you what is the small f, so you don't need to worry about that. You just plug in the formula. But in general, you may have difficulty to find this f, so we need to find some general procedure to derive the potential function. Okay, so first recall, notice that if we change this formula a little bit, so you can rewrite f gamma b is f gamma a plus integration f times dr. Okay, and next, so therefore if we view b as a variable, and on this side we view view a as a constant, then you have the formula. So no matter what the right hand side is, it's a function of b. So you derive the formula for this potential function f by this formula, by this form. Okay, therefore we need to calculate this. Okay, then so recall that before we said here the parameter a and b are not important. The important thing is the gamma a and gamma b, the coordinates for the initial and the ending points. Okay, so we can write down this as following: fxyz is fx0, y0, z0, and plus integration along some curve xyz f dot dr. Here we need to explain a little bit what is xyz and what is cxyz. So here x0, y0, z0 is the coordinate for gamma a, so the initial point, and the xyz is a coordinate for gamma b, vary ending points, and CXYZ any curve connecting starting from x0, y0, z0, ending at xyz. Okay, if you draw a picture, you have this one. So let me draw this. So this is your domain, and this point x0, y0, z0, and here you have xyz. And so in this case, let's choose one xyz. So this is case 1, one choice for xyz for this curve. And we also have the following choice for the curve connecting x0, y0, z0, and xyz. You might choose this one and then this one. Okay, oh sorry. Recall this is in 3D, so the coordinates here is x, y0, z0. Here is x, y0, z, and go this way. Also, you might have some other choices, and even the very arbitrary one. Okay, if f is conservative, the choice of CXY does not affect the final answer. In other words, we can choose any path we want to calculate the integral on this side. Okay, so usually I will choose this one. So let me denote this as 1, 2, 3. So remark, I will choose first pass in general because although the computation are a little bit involved, but it's straightforward. It's just one step, one-dimensional integral. Your textbook, see a different approach. In your textbook, use basically they are using the path in case 2. Okay, so I will show you the general procedure to carry out the calculation. So first, if our f, suppose now into the previous formula works for 2D and 3D, even in ND, so it doesn't matter. I plus x squared minus 3y squared j, and find f such that capital F is gradient f. And the problem B is calculate certain integral. So here f is as above, but here c is explicitly defined curve. So sine exponential t sine t is first coordinate, exponential cosine t j, and the t is from 0 to pi. Okay, so before we do calculation, it's easy to find that B is an easy corollary of A. As soon as you figure out what is a potential function, you just plug in the data of two endpoints, data of two boundary points. Okay, so we first look at A. And for simplicity, we can also choose the starting point we like. So fix x0, y0 to be the origin, and then the xy just any point in R2, and then let's construct this cxy as a straight line connecting these 2 points. Okay, so next we parameterize. Take cxy to be 1 minus t times 0, 0 plus t times xy. Okay, so here your parameter is xy, and then you find out right, so here I need to fix some notation. This is a little bit confusing part, but I hope you can get it. So as soon as you choose the ending point, you name it capital X and capital Y, you cannot change it. Now, if you still want to use small xy for the coordinate function, then you should have the following one. So this is a little bit confusing part. But it's confusing not because the idea is not clear, but because we have the convention we want to use xy for the coordinate function and for the ending point. So you need to distinguish these two cases. Okay. So anyway, you will have this situation by calculating the above. And just recall, this is x coordinate for the ending point. Similarly, this capital Y is a y coordinate for the ending point. And the xy just a general point on this yellow line. So coordinates for any point on cxy. Okay, sorry. Here probably you better use this notation. Yeah, this is correct. This is correct. Okay, then of course t is between 0 and 1. Then what do you have? Then fxy. Recall this is value at the ending point xy. Okay, and by this formula, so it's f 0, 0 plus integration along cxy, and then you have fdr. F is so let's write one more step, dr. Okay, next let's compute each terms, and actually from this one you get dx dt is capital X, dy dt is capital Y. Okay, and then this one, when you plug in 0, 0, because your function, your vector looks like this, so this is 0. You only have the second part, cxy. And for cxy, you can, this is just a line integral of second kind. You can reduce it to one integral in one variable. So here you have 3 plus 2x times ty. This is because you have this term here. You just plug in, and then times dx dt. Therefore, you have times x, and then secondly, you have here you have x squared minus 3y squared. So tx squared minus 3ty squared, and dot dy dty and dt. And here, remember, view x, y as constant. We're only integrating with respect to t. Okay, and so to indicate this, so I will write tx, ty, tx, ty, y. Okay, then what do you have? You have, let's simplify a little bit. You have 0 to 1, and first, so here you have x. So first you have 3x plus 2t squared x squared y plus t squared x squared y minus 3t squared y cubed dt. Okay, then what do you have? You have 3t x plus 2t cubed over 3 x squared y plus t cubed over 3 x squared y minus t cubed y3 and evaluate at 1 and 0. And when you plug in 0, you have nothing. When you plug in 1, you have 3x plus x squared y minus y cubed. Okay, so now xy is three x plus x squared y minus y cubed. Okay, since the capital X, capital Y, just two free variables, okay, then you can, usually we just use small xy to represent it, is a potential function. Okay, here a small remark. You might derive a different potential function which is fxy plus some constant. This is okay. Because we showed before, for potential function, if you adding it or subtracting a constant, then you take gradient. It still give you the same gradient vector field or conservative vector field. So the potential function is not unique. Just like the indefinite integral, the answer is the antiderivative is not unique. They're unique up to a constant. Okay, and if you don't like this method, you can turn back to your textbook for another one. So that method, you don't need to use a lot X, capital Y stuff. You are doing repeatedly antiderivatives, but you need to do it 3 times and with different variables. So personally, I prefer this one, but it's all up to you. Okay, now let's look at B. Then B is easy. So no matter what curl C you have, you just use generalized Newton-Leibniz formula. And notice that for our curl B, so the initial is 0 when t is 0, so it's 0, 1, and the ending when t is pi, so exponential pi sine pi, which is 0, and negative exponential pi. Okay, so here you have 0 exponential, negative exponential pi minus f 0, 1. So recall f is given by this, so you have negative exponential pi cube minus negative 1/3. So exponential 3 pi plus 1. This is the final answer. Okay, now let's look at another example in 3D. So if capital F, x, y, z is given by y squared 2xy plus exponential 3z, 3y exponential 3z. Find f such that gradient f is capital F. So similarly, we draw a picture and x, y, z. So next, fix x0, y0, z0 to be 0, 0, 0, and curve CXYZ is parameterized by x equals tx, y equals ty, z equals tz, and t is between 0 and 1. And now, by our formula, the f capital X, capital Y, capital Z can be computed by f 0, 0, 0 plus integration c over cxyz f dot dr. And notice the function, when you plug in 0, 0, 0, you have 0, so you don't need to consider this one. And you only need to figure out the line integral for this specific curve. And notice that from this parameterization, you have the derivative. Okay, therefore for this one you have integration from 0 to 1 f, so you have y squared, so t capital Y squared times dx dt plus 2xy, so 2xy, 2xy plus exponential 3z times dy, so it's y, and then plus, so this what is 3y exponential 3z, so 3y exponential 3z times z. Okay, so yeah, that's it. And this is first part, the second part, the third part, and finally you integrate with respect to t. Okay, now let's do it one by one. So first simplify. So 0 to 1 t squared xy squared plus 2t squared xy squared plus y exponential 3tz and plus 3tyz exponential 3tz dt. Okay, let's these two are same, so you can combine these two. So you have t cubed xy squared and then plus. For this one, sorry, for this one you have y exponential 3tz over 3z. Okay, and then for the last one, you have remember you view capital Y, capital Z as constant. So this is a function like exponential function times a polynomial. By integration by part, you can derive the following: exponential 3tz divided by 3z times 3tyz minus y exponential 3tz divided by 3z. This and leave it to you to verify. Okay, then you need to plug in 0 and 1. And when you plug in 1, you have x y squared plus 3z exponential 3z over 3z plus exponential 3z over 3z times 3yz minus so here you have y actual y minus y exponential 3z over 3z. Okay, and then you have when you need to plug in 0. So minus, when you plug in 0, so here you only have this one, so y over 3z, and this one, and this one, minus y over 3z. So finally you have x y squared plus, so remember this cancel out with this cancel out with this, plus and exponential 3z times y. Okay, and next we want to turn back to 2D. We finish up with general formula for finding the potential function for a conservative vector field. Now we turn back to 2D. So the leading question is, so recall how to determine if f is conservative or not. And before we already know, so there's some necessary condition. Curl f is 0. Necessary condition means if f is conservative, then curl f is 0. Okay, especially in 2D. So what do we have? In 2D, recall f can be written down as pi plus qj. And to apply the formula in 3D, because we only define curl in 3D, so this is in 3D. So we add actual 0k here. You view this vector field as a three-dimensional thing, but the last z coordinate just trivial. It's okay, so you just embedding it into 3D. And then let's compute what is the curl f for this extension. So you still have this formula, and you have ijk, so partial x, partial y, partial z, p, q, and recall the last one is 0. Okay, then we can do calculation. So I negative partial z q here I should make a remark. So this p just pxy. This q is also qxy. They do not depend on the third variable. And similarly for j, you have minus j minus partial z, partial pxy partial z, and then lastly you have k partial q partial x minus partial p partial y. And recall, because you are taking z derivative, this is gone, this is gone. This by the partial derivatives, we view x, y as a constant when you're taking z derivative, so nothing left. And therefore, no matter what your vector field in 2D is, finally, the curl will be in the third direction, and then the component is given by this. Okay, therefore we have the following. We first make the following definition. So this is curl in 2D. So let f equals pxy qxy, a vector field in 2D. Define curl f to be qxy partial q partial x minus partial p partial y. And here I would like to make a remark. Curl f in 2D is realized by a scalar function. So we usually see curl f in 2D, view that as a function, although in general it's a vector field in 3D. So the reason is clear, because, so I should say, it does not contradict with the fact curl f in 3D is a vector, because curl f in 2D has a fixed direction k. So if you know the direction, so how to describe a vector, you only need to know its magnitude. So here the direction is given. You only need to know the magnitude here. Therefore, a slightly abusive convention, we always view curl f as a function in 2D. So I hope you understand this part. Okay, next we have the following theorem. So fxy, suppose this is just the notation. So you write f in components as the following, and if f is conservative, or equivalently we say the integral is independent OC with fixed boundary points. Equivalently, we show that these two are equivalent. Then we must have this equality. So the proof is easy because we know curl is conservative. Curl F is 0. And therefore, what is curl F? Partial Q, partial X minus partial P, partial Y equals 0. Then you have this one. Just another way to narrow down the curl condition, the necessary condition, curl F equals 0 in 3D to in 2D. Okay, you have this numerical criterion. And we would like to know when this is true inversely. Inverse. So if D is a simply connected region, I will show you the example of simply connected region, but it's impossible to define it rigorously in our class. So basically, you can view it as no hole in R2. Okay, recall. So far, we only care about the 2D case. And you have this necessary condition. On D. Then dr is independent OC only depend on the boundary points. So remark, let's show some example. This is simply connected. Simply connected because there's no hole. And also, so the whole region R2 simply connected. And non-example, this donut is not simply connected. Therefore, you cannot apply the theorem for donuts. And then of course, you can have this ghost face. This is not simply connected. Okay, and so the theorem, what does the theorem really mean? That if you have, so let's make second remark. If D is good enough, the region is good enough, simply connected. F curl F is 0, then F is a conservative vector field. Or you can, in practice, how we apply this theorem. Suppose you want to compute the line integral C1 FDR. You can deform it to, so this is C1, C2, and etc. deform all the way to C star. Okay, later on I will give you some example showing this how to apply this formula. But then before that, we would like to discuss a more general question. So far, we only consider conservative vector field F, okay, in this lecture. So in particular, we derive some other method to compute the line integral of second kind besides the one by definition. For example, we show that you can first compute the potential function and then evaluate, or you deform the path. But that's only true for conservative vector fields. Okay, now we like to ask similar question. Can we find an alternative way to calculate the line integral of the second kind when f is not conservative? It's a natural question. But then the answer, as you can expect, not that easy. So the answer, we have to put on some actual condition. In general, it cannot be true. Okay, so the condition. So therefore, in the following, we consider the following case. In the following, we consider the case consider the following case. We will consider the case when D, the region, is in R2, but it's not necessary to be simply connected. And the curve C is closed, so there's no boundary point. Okay. So what does that mean? We will consider the following cases. Suppose this is your region, might be very weird, and we consider the curve. You can consider this curve starting and ending at the same point, or this curve, or union of them. But basically you can decompose them into a simple one. Okay. So we would like to state the Greens Theorem. Suppose for the proof, I will either give it at the end of this course or just omit it. I think the most important thing for in this stage is to use that to apply the formula. So let F be P Q in R2, and then C is count clockwise oriented. I will talk about the orientation just in a moment. Curl. Then you integrate F along C, the second kind. This is equal to double integral over the region R. So inside you have partial Q, partial X minus partial P, partial Y, dx dy. Here, R is the region enclosed by C. And so the remark we can rewrite the star as this one, curl F dA. So this quantity just curl F, and this is the second kind, the line integral of F, that line integral of second kind. Okay, if we draw a picture, then what does it say? So you might have some holes here, and okay, I should assume this is simply connected. Sorry, it's simply connected. Okay, so the situation would be like, this is your region might be bad, and this is your curl, and the region enclosed is given by this. Okay, so the integration of C equals to the integration double integral of curl F dA over R. And here the orientation means counterclockwise, so you go this way. Just make sure when you walk around along C, R is on your left side. Okay, so this is one piece version. There's some other piece. There's some other version for multiple piece. So we can stay here. Still Greens theorem. So now let's define it in the other way. If R is a domain in R2 and whose boundary consists of C1 all the way to Cm, where each Ci is defined is a curve with certain orientation, compatible. So the compatible just means this one. Then the double integral curl f dx dy equals to the summation Cii from 1 to m f dr. Okay, so here we draw a picture what it look like. Now your region can be where, and also your domain. It's not necessary to your R, not necessary to be simply connected. For example, you can take this as your R. Then you have four boundaries. So this is one over the boundary. 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 And then the orientation is given by this. And inside, you do clockwise because you need to make sure when you walk around, the domain is on your left side. So let's denote this as C1, C2, C3, C4. Okay, then you can correspondingly write down the integral on this side. And we will do some example later, just in a moment. So this is a general idea. Okay, so let's look at example. So evaluate. Recall this Greens theorem just give you an alternative way to calculate one of the sides, but sometimes you can just compute it directly without using Greens theorem. Curve consisting of the line segment from 0, 0 to 1, 0, 1, 0 to 0, 1, and 0, 1 to 0, 0. Okay, so you have this situation. Solution. Method 1. Compute line integral, the line integral directly. So I will not carry out this method. Method 2. So recall the orientation is given by from 0, 0 to 1, 0. So go this way. Okay, so this is your C with this orientation. And therefore, by the formula C Greens Theorem, FDR, this given by, let's call this as R, curl F dx dy. Notice that here, since the line integral along the C, the orientation is the same as the one required in the formula. Therefore, this formula is true. Otherwise, if the one you need to compute goes the other direction, then here you need to have minus sign. We will deal with that case later. Okay, then here you need to figure out what is the right hand side. So but right hand side, is not that complicated due to the shape of the domain. And then you recall, before we do that, curl is partial q, partial x minus partial p, partial y, dx dy. Then what do you have? Actually, you have integration of y dx dy. And then if you write down, you view it as type 1 domain. So x is from 0 to 1, and y is from 0 to 1 minus x y dy. So therefore this is 0, 1 dx y squared over 2, 1 minus x 0. So 1 minus x squared over 2 integration with respect to x. So x minus 1 cubed over 6, 1 and 0, and then you have it's 1 over 6. Okay, now another example is the following. It's the following. Let's compute. So here, when this is a notation, when you want to indicate C is a closed curve. Okay, so 3y minus exponential sine x dx plus 7x plus y to the fourth plus 1 dy, and where C is x squared plus y squared equals 3 squared count clockwise oriented. So the solution, let's draw a picture. So due to the Greens theorem, what do you have? Greens theorem. Integration f dr along C, so this is C, equals to integration curl f dx dy on R. So this is R. And you need to check the orientation because it's counterclockwise, so this formula is true. And then let's compute the right hand side, and let's first write down R. So curl partial P minus partial Q, partial X, partial P, partial Y, dx dy. So finally, this is R7 minus 3 dA. And notice this is a disk with radius 3, so you can just write down the area. So there will be area of R. So 4 times pi r squared, so 36 pi. So if you want to summarize why we choose Greens theorem, that is because the formula, this one, and this one hard to compute the integral, but then if you use Greens theorem, take a derivative, there happens to be the term that involved in the formula cancels out. Okay, so that's a good point. You have some hard part, and then if the Greens theorem just kill out this hard part, this difficult part, then you should apply that. Okay. So another one I want to mention is the following example. So suppose F is given by this vector field. And this vector field is very special, so I should make a remark. Very special. And the reason is it's the real part and imaginary part of the complex, or some very simplistic function, 1 over z, when z is a complex number. But we will not talk about this. This is too advanced. But I mean, so here you cannot do some arbitrary perturbation of the coefficients. Otherwise, it's not true. Okay, and the job is compute, or just compute the line integral this way, where C is given by, so I draw a picture instead of C. Two, negative 2, negative 2, negative 2, 2, negative 2, 2. And then you have some orientation. Okay, so the solution. Method 1, direct calculation. You should get the answer. Okay, method 2. It's a little bit involved because you have to calculate the antiderivative of 1 over 1 plus x squared, which is arctangent. A little bit involved, but not that much. It depends on the shape of the curve. If I deform it further, it's more weird. Then you have a harder time to calculate. Okay, the method 2 is we want to apply the want to apply Greens Theorem. But here you need to be very, very careful that it because the function f is not defined on 0, 0. This is a fact we proved before. We showed that the function is not continuous at origin. So this point has no definition. Therefore, yellow part is not the region enclosed by green curves. You have some ambiguity inside it. So therefore, we choose a small circle to cut it. Okay, or we choose another to cut it. So we call this as C2. So strategy, consider the region enclosed by C and C2. Okay, then apply the so consider region, let me call it R. Now apply the Greens theorem. What does that tell you? You have curl f dot dx dy equals the integral along C1 with the C along the positive orientation plus C2. Notice that C2 has a different orientation. Okay, so if you so now let's figure out each term. So first, let's compute curl f. So what is curl f? So it's partial x squared plus y squared partial x minus partial minus y over x squared plus y squared over partial y. So this is 1 over x squared plus y squared minus x squared plus y squared 2x squared and plus 1 over x squared plus y squared minus x squared plus y squared squared 2y squared. So the answer is 0. So that means here this is 0. Therefore, integration f dr along C is negative dr along C2. And if we draw the picture for C2 again, because C2, the orientation is go this way, and this is C2. Before we said this is equal to negative C2. So what is the negative C2? I drew it on another graph. The trace is the same, but then you just inverse orientation. So negative C2. Okay, now, so remember this. So we choose C2 small enough and then use polar coordinates to consider this one. And now take, so let negative C2 be a curve parameterized by, for example, x is, you take the small radius, for example 1/2, to make sure it's inside the big, inside the box, the square. So cosine theta y is 1/2 sine theta. Okay, and in particular dx d theta is 1/2 negative sine theta. dy d theta is 1/2 cosine theta. Theta is between 0 and 2 pi. Okay, now let's consider negative C2 f dr. So the integration with respect to theta will be from 0 to 2 pi, and f is, recall it's negative 1/2 negative y over x squared plus y squared times dx dt, so negative 1/2 sine theta, plus x, so 1/2 cosine theta divided by 1/2 x squared plus y squared times what is the next part is dy d theta is 1/2 cosine theta d theta. Okay, then if you compute it, you find this is 0 to 2 pi 1 d theta, it's 2 pi. And actually, it's a general fact. No matter what c is, the integral over c is a multiple of 2 pi. Okay, I will stop here.